Gravity, an invisible force, governs the cosmos. It is the unseen hand that shapes the universe, influencing everything from the smallest particles to the largest galaxies. It holds us to the Earth and dictates the motion of celestial bodies. Every step we take, every orbit of a planet, is a dance choreographed by gravity. Without gravity, stars, planets, and galaxies would not exist. It is the glue that binds the cosmos together, allowing stars to form and planets to orbit. Our very existence is a testament to its power. From the way we move to the way we gaze at the stars, gravity is an ever-present force in our lives. Understanding gravity is fundamental to unraveling the mysteries of the universe. Scientists and researchers dedicate their lives to studying this force, hoping to unlock the secrets of the cosmos. Gravity is a universal force that attracts any two objects with mass. This attraction is what keeps us grounded and what causes objects to fall. The more massive an object, the stronger its gravitational pull. This is why massive planets like Jupiter have such a strong influence on their surroundings. The closer objects are, the stronger the attraction between them. This principle explains the orbits of planets and the behavior of objects in space. This simple yet profound concept explains why planets orbit stars and why apples fall from trees. It is a fundamental principle that governs the motion of objects. Gravity's influence extends far beyond our planet. It reaches across the vast expanse of space, affecting distant galaxies and shaping the universe. It binds the moon in its orbit around Earth. This gravitational pull is what causes the tides and influences our planet's stability. It orchestrates the intricate dance of planets around the sun. Each planet follows a precise path, guided by the gravitational pull of the sun. Gravity is the architect of the cosmos, shaping the large-scale structure of the universe itself. It is the force that has sculpted the universe into the magnificent tapestry we observe today. The quest to understand gravity has captivated thinkers for centuries. From the ancient Greeks to modern physicists, the journey to unravel the mysteries of gravity has been long and fascinating. The ancient Greek philosopher Aristotle believed that objects had a natural tendency to move towards the center of the universe, which he believed was Earth. His ideas were based on observation and philosophical reasoning, rather than experimental evidence. This idea prevailed for centuries, shaping the way people understood the natural world and the cosmos. In the 17th century, Galileo Galilei challenged Aristotle's view. Using his keen observational skills and innovative experiments, Galileo began to question the long-held beliefs about motion and gravity. Through his experiments with falling objects, Galileo demonstrated that objects accelerate at the same rate regardless of their mass. This was a monumental shift in understanding, laying the groundwork for future scientific inquiry. This groundbreaking discovery paved the way for a new understanding of gravity, challenging the established norms and encouraging others to explore further. Sir Isaac Newton revolutionized our understanding of gravity in the late 17th century. Building on Galileo's work, Newton formulated the universal law of gravitation. He proposed the universal law of gravitation, which stated that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. This law explained not only the motion of falling objects, but also the orbits of planets and the behavior of celestial bodies. In the early 20th century, Albert Einstein further revolutionized our understanding of gravity with his general theory of relativity. Einstein's theory provided a new framework for understanding gravity, one that went beyond Newton's laws. Einstein proposed that gravity is not a force, but rather a curvature in the fabric of space-time caused by the presence of mass and energy. This idea transformed our understanding of the universe, influencing everything from the study of black holes to the expansion of the cosmos. Gravity's influence is all around us, shaping our daily experiences in ways we often take for granted. It's the reason why objects fall to the ground when dropped, whether it's a ball, a leaf, or even a piece of paper. It keeps us grounded on Earth and prevents us from floating away into space, allowing us to walk, run, and jump with ease. Gravity also plays a crucial role in our everyday experiences, from the way we move to how we interact with our environment. The feeling of weight is due to gravity pulling us towards the center of the Earth, giving us a sense of our own mass. It's why we feel heavier on Earth than we would on the Moon, which has weaker gravity, making movements there feel lighter and more buoyant. Gravity also affects the flow of fluids, guiding water from high places to low, ensuring rivers flow and faucets pour. Tides, the rise and fall of ocean levels, are caused by the gravitational pull of the Moon and the Sun, creating rhythmic patterns in our oceans. The Moon's gravity is stronger on the side of Earth facing the Moon, causing a bulge in the ocean, which we observe as high tide. A corresponding bulge occurs on the opposite side of Earth, creating another high tide, demonstrating the powerful and far-reaching effects of gravity. Newton's universal law of gravitation provides a mathematical framework for understanding the force of gravity. It states that the force of gravity between two objects is directly proportional to the product of their masses. This means that more massive objects exert a stronger gravitational pull. The force of gravity is also inversely proportional to the square of the distance between the centers of the two objects. This means that the force of gravity weakens rapidly as the distance between objects increases. Newton's law explains why planets orbit stars in elliptical paths. The star's gravity pulls on the planet, keeping it in orbit. The planet's velocity keeps it from falling into the star. Section 5. Einstein's revolution. Gravity as warped spacetime. Einstein's general theory of relativity revolutionized our understanding of gravity. Einstein proposed that gravity is not a force but rather a curvature in the fabric of spacetime caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The ball's mass causes the trampoline to sag. Similarly, massive objects in space warp the fabric of spacetime around them. Objects moving through this warped spacetime follow curved paths, which we perceive as the force of gravity. Einstein's theory provided a more accurate description of gravity than Newton's law, especially in strong gravitational fields. It also made several predictions that were later confirmed by observations. Section 6. Evidence of gravity's influence. From falling apples to distant galaxies. Numerous observations and experiments support both Newton's and Einstein's theories of gravity. The falling apple that inspired Newton is a classic example of gravity in action. The apple falls towards the Earth because of the Earth's gravitational pull. The motion of planets around the Sun provides further evidence of gravity. Kepler's laws of planetary motion, which describe the elliptical orbits of planets, can be derived from Newton's law of gravitation. Gravitational lensing, the bending of light around massive objects, is a prediction of Einstein's theory of relativity. Astronomers have observed gravitational lensing around galaxies and clusters of galaxies, confirming Einstein's theory. Section 7. Gravity's grand design, shaping the universe. Gravity plays a fundamental role in the formation and evolution of the universe. It caused the early universe to clump together, forming stars and galaxies. Gravity holds galaxies together in clusters and superclusters. Gravity is also responsible for the formation of stars. Clouds of gas and dust collapse under their own gravity, heating up and eventually igniting nuclear fusion in their cores. The expansion of the universe, discovered in the early 20th century, is also influenced by gravity. The gravitational attraction between all matter in the universe slows down the expansion. Section 8. Black holes. Gravity's ultimate triumph. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. Black holes form when massive stars collapse at the end of their lives. The boundary of a black hole is called the event horizon. Once an object crosses the event horizon, it can never escape. Black holes are a testament to the extreme conditions that can exist in the universe. Astronomers have detected black holes indirectly by observing their effects on surrounding matter. For example, gas falling into a black hole heats up and emits X-rays, which can be detected by telescopes. Section 9. Unraveling the mysteries. Dark matter and gravitational waves. Despite our understanding of gravity, many mysteries remain. One of the biggest mysteries is dark matter, an invisible form of matter that makes up about 85% of the matter in the universe. Dark matter does not interact with light, so it cannot be observed directly. However, its gravitational effects are evident in the rotation of galaxies and the large-scale structure of the universe. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, are another prediction of Einstein's theory of relativity. Gravitational waves were first detected in 2015, opening up a new window into the universe. Section 10. The future of gravity research. Quantum questions and cosmic puzzles. Gravity remains one of the most active areas of research in physics. One of the biggest challenges is to unify gravity with quantum mechanics, the theory that describes the behavior of matter at the atomic and subatomic levels. Another area of active research is the study of black holes. Scientists are working to understand the properties of black holes, such as their entropy and information content. The detection of gravitational waves has opened up new avenues for studying the universe. Gravitational wave astronomy has the potential to reveal insights into the early universe, black holes, and other extreme phenomena.